Welcome to our introduction of electromagnetic induction. In the last chapter we saw how a conductor carrying current produces a magnetic field. Let me show you a quick animation of that. So here we have a bunch of compasses arranged in a circle around here and this wire. Currently there's no current running through the wire, but if I were to add current, you'll see suddenly the magnets will arrange in this circular form. And if you use the right hand rule with your thumb pointing in the direction of the current, your fingers will curl in the direction of the magnetic field. Hence, if I make the current go downwards, then we see that we have now a magnetic field now going clockwise. This idea of a conductor carrying current producing a magnetic field was first discovered by Hans Christian Ørsted, when he noticed that a compass needle became deflected by a current-carrying wire. Soon after this discovery, scientists started to search for further links between electricity and magnetism. And it was in 1831 that Michael Faraday discovered that he could produce electric currents by varying the magnetic field. In one of Faraday's first experiments, which are not shown in the notes, but shown now below, he connected a coil wire, so this is a coil wire, to a battery, and then a switch. And on the other side over here or nearby, there was another coil wire connected to a current meter. When he closed the switch in the first circuit, he noticed that current was momentarily produced in this second coil. This current only appeared when the magnetic field was changed. However, when the circuit was closed and there was a steady current, the second circuit over here had no induced current. And then when he opened the switch once again, current was induced, but in the opposite direction. So Faraday concluded from this experiment that when there's a steady current flowing through this circuit, it produces no current. However, a changing magnetic field by either closing the switch or opening the switch will produce momentary electrical currents. This phenomena is known as electromagnetic induction. In another experiment, which is often shown in many textbooks, he used a magnet, a coil wire, and an ammeter, or a galvanometer, which is a very sensitive ammeter. When he moved the magnet into the coil wire, he noticed a current was induced in the ammeter because of the increasing magnetic field as this magnet approached the coil. When the magnet was moved away from the coil, current was induced in the opposite direction due to the decrease in magnetic field. I'll show you a few demonstrations in class, but here's a quick video as well. This is a quick video from MIT videos that are available online for free, and there are other resources. So what we have is a coil wire hooked up to a galvanometer, which is a very sensitive ammeter, and then a very strong magnet. I'll be showing you this demonstration in class, but here's a video clip of it. So watch as this magnet is thrust into this loop and see what happens. So here it moves forward and you can see the deflection of the needle. Now it's about to be moved to the left here, and you see now it's starting to deflect in the opposite direction. Let me continue, press play, and there you go. So you can see that as it moved forward into the loop, the current was induced in one direction, and then when it stopped moving, then it went back to zero. And then as you pull the magnet away, then current was induced in the opposite direction. So once again, I'll play the video for you to observe again, in case you missed it. So hopefully after viewing this video and seeing how this experiment works, one can conclude that the motion of the magnet relative to the coil is required for current to be produced. From Faraday's experiments, you can see that a changing magnetic field as it's thrust in or pulled out will induce a current, and hence the coil essentially behaves as an EMF source, even though there's no battery connected to the coil whatsoever. To explain this phenomena mathematically, we need to introduce the concept of magnetic flux. Let's consider we have a magnetic field shown here in blue that passes through an area A that is bound by some conducting loop. The magnetic flux, which is represented with this phi sub b, is found to be proportional to the number of lines that pass through this loop. Conceptually, it's really just how effective these magnetic field lines can penetrate this area A. The magnetic flux is the dot product between the magnetic field vector and the area vector. The direction of the magnetic field is in the same directions of these blue lines, and the direction of the area vector is normal to the surface, which means it's perpendicular to the surface. If you recall, the dot product between two vectors, say A and B, is equivalent to the magnitude of A times the magnitude of B times the cosine of the angle, sometimes written as this. So the magnetic flux formula is given by this formula shown in the box. Its symbol here is called phi. So this is phi sub b equals the magnetic field strength B multiplied by the area of that is bound by the loop A multiplied by cosine of theta, which is the angle between the normal of that plane, which the area vector points in, and the magnetic field B. The SI unit of magnetic flux is in Teslas for magnetic field multiplied by the area, which is meters squared, and we call these units of Tesla meters squared as Webers, named after Wilhelm Weber. Now let's consider a few cases where we get maximum and minimum flux. If the magnetic field penetrates the surface perpendicularly to the plane, as you can see with this right angle here, then we find that the magnetic flux is equal to B times A. Remember that the magnetic flux formula is VA cosine theta, but in this case our angle is 0 degrees. It is 0 degrees because the magnetic field lines are parallel to the normal or the axis of this plane. Hence the angle of theta here is 0 degrees, and so we get cosine of 0 degrees, which is really just 1, and hence we get the magnetic flux being equal to simply B times A. Now let's suppose that we take this plane loop and we were to rotate the loop. So now that the magnetic field will penetrate the loop at some angle theta to the normal. How would we calculate the magnetic flux? We would use just this formula where theta would represent the angle between the field lines and the normal to the plane. Hence it becomes the phi sub b equals BA cosine of theta. And in our last case shown over here, we see the magnetic field lines are parallel to the loop. The magnetic flux in this case turns out to be equal to 0. Let's go back to our formula. Phi sub b equals BA cos of the angle between the B field and the normal. And in this case, that will be 90 degrees. And the cosine of 90 degrees is 0. So the magnetic flux in this case will be 0. There'll be no flux. It'll be a minimum. Notice that the field lines are not penetrating this surface whatsoever. Hence, since they're not able to penetrate the surface because they're running parallel, there will be no magnetic flux. We are using this magnetic flux definition to summarize Faraday's law. If you flip ahead to page 4 in your notes, you'll see Faraday's law of induction. Faraday's law states that the induced EMF, or current, but in this case we're looking at the EMF, represented with epsilon, remember this is measured in volts, is directly proportional to the change in magnetic flux. The EMF induced is given by this formula. Epsilon equals minus the change in the magnetic flux divided by the time interval delta t. This is the magnetic EMF that is induced for one single loop. if you have more than one loop, you have, say, n loops, the EMF induced will be equal to negative n times the change in magnetic flux divided by the time interval delta t. This equation, which is on your AP formula sheet, is known as Faraday's law of induction. So the EMF induced depends on the change in that flux over time. And the change in flux will depend on the magnetic field B, the area that is bound by that loop, and the angle between the magnetic field and the normal to the plane. So if we vary any of these three quantities over time, magnetic flux will change, and hence an EMF will be induced, and hence a current will be induced in the loop. As you can see in A, we have a magnetic field that is going into the page or into the screen, and we have a plain loop. And now you see fewer x's, which means the magnetic field is decreasing at a later point in time. This decrease in magnetic field, and hence magnetic flux, causes a current to be induced in this direction. In the picture B, you see we have a loop where we stretch it, causing the area to decrease. You can see that there are like 6 x's in here and maybe about 4 x's that are penetrating in this loop. So the area is decreasing, which is causing a decrease in the magnetic flux, which will then cause that change in magnetic flux will have an EMF that is induced in the circuit as shown below. And lastly, in part C, we have this loop that is on this axis, and the loop is rotated within this constant magnetic field. As the loop rotates, the angle theta changes. And hence, because the angle theta changes, the magnetic flux changes, and we have an EMF and current that is induced in this circuit. So now you should be ready to tackle some problems.